Nowadays, privacy has become a vital problem for mobile applications, especially for personal photos and hospital scenarios. Ideally, we can inference the model all on the edge device without any data leakage. But the tight resource constraint limits the capacity of the models. The cloud server is another choice for large model inference, but there will be serious privacy issues when the cloud is not trustworthy. Instead, our method utilizes the linearity of neural networks to encrypt both the input and output. It mediates between the resource-constrained edge devices and the privacy-invasive cloud servers. The edge device first preprocesses a group of input images and encrypts them by linear combination with private random coefficients. Then the encrypted inputs are sent to the cloud. The cloud feeds it into the main model and sends back the outputs to the edge device. Finally, the edge device decrypts the output with the private coefficient and gets the results. In our demo, we will show our efficient accuracy and privacy-preserving cloud edge inference framework for facial attribute classification. On the screen, the left side is the dashboard of the edge device, and the right side refers to the monitor of the server. Firstly, the user uploads 8 images to the edge device. Our method encrypts the images by an efficient linear combination on the edge device with a random coefficient as the private key. The mixed images are then sent to the server one by one and passed into the inference model. Since the model is trained in an encryption-aware manner, the output is still encrypted. Without knowledge of the private key for mixing, the server cannot have any information from both the encrypted inputs and the outputs for every single image. The server will send back the intermediate output of each image to the edge device. Finally, by using all 8 outputs, the edge device can then decrypt the result for each image with the private key. Each column of the labels in the blue box denotes the prediction for one of the facial attributes, and the visualization results in the red box show the prediction for each input image decrypted from the output. Our method accurately predicts the facial attributes for each image without leaking information. For example, in the 4th image, the model correctly classified that the man does not wear glasses, but the encrypted output gives a totally different result. We also designed a GAN-based attacking method, to evaluate the effectiveness of each defending methods. As we can observe in the figure, adding noise fails to hide many details and personal identifications. Blurring cannot remove some of the sensitive face attributes, such as race, and hair color. On the contrary, our FaceMix successfully protects all private information. The attack model fails to reconstruct the faces from the encrypted inputs. To sum up, our method enables large models for resource-constraint edge devices, delegating most of the model computation to the cloud, without sacrificing accuracy or privacy. In the future, it can also be applied to other modalities, like language and speech, since the encryption and decryption functions are not specified for a single task.